Today we're going to be looking at quadratics in the real world. You will be able to apply characteristics of quadratic functions to real-world situation. You can identify the practical domain and range of a quadratic function given a situation. Now, have you ever heard of pumpkin chunking world championships? Well, they have them in Delaware, and they started on 21 years ago. And so here's a little bit about a pumpkin chunking world and championships in Delaware. And this is located in on the YouTube.
On a bone-chilling November morning near the Delaware seashore, massive cannons and catapults are being assembled as if the nation was preparing for battle.
Fire in the hole, fire in the hole.
But this arsenal won't be used to combat enemy raiders or for historic war reenactments. These weapons are being made exclusively for throwing pumpkins.
So this is the Second Amendment, and this is absolutely the baddest pumpkin gun on the planet.
The Pumpkin Chunkin' Festival was started 20 years ago near Millsboro, Delaware, with 3 slingshot-style machines shooting pumpkins in someone's backyard. Little did the founders know that this first event would inspire a veritable arms race. Today, 100 teams are stationed on the front line, preparing to see how far their self-designed weapons can launch a pumpkin across a 280-acre cornfield.
In 1986, there were 4 guys sitting around the local blacksmith shop discussing medieval games, specifically anvil tossing. They rapidly found out that was rough on the back and shoulders, so they decided they could build a machine to throw it. Anvils were expensive, they bought pumpkins, and here we are 21 years later throwing pumpkins at the World Championship pumpkin chunking.
The machines range from high school physics projects made from junkyard scraps to high-tech blasters that can cost upwards of $200,000. Although explosives are forbidden across the board, many of these machines still pack quite a punch. Because of the wide variety of contraptions, the competition is divided into different classes.
What we consider the big boys of the competition are the air cannons. Of course, all those guys are looking for what we refer to as the mythical mile.
The air cannons work by sending a rush of compressed air into the barrel, which rockets the pumpkin out the other end. These cannons can launch pumpkins over 4,000 feet, about the length of 11 football fields. And this year, current record holder Second Amendment is gunning for the mile mark at 5,280 feet.
Current world record is 4,434 feet. In practice last weekend, we shot one over 5,000 feet.
Another team going for gold today is Team Chucky, a team that will be competing in the torsion catapult division.
Torsion catapult is what most people think of when they think of like an old-fashioned Roman catapult. And what it is, there's a bundle of rope that gets twisted, and tension gets put into it, and so the rope becomes a torsion spring. And it's that tension stored in the bundle of twisted rope that makes the arm go forward.
So this is a Pumpkin Chunkin' World Championships, and since this was created, there have been, I'm sure, lots and lots of more different kinds of pumpkin chunkin' calipos that they've come up with. It'd be interesting to see what they have. Now, we're going to go on, and so look at this right here. What do you think the world record for pumpkin throwing is? Any idea? Well, how would they do it? How could you mathematically model this situation? Well, here is, at this time that this was created, the world record for the pumpkin throwing was 4,623 feet. It'd be interesting to see if that record still holds today, or how more advanced technology has become since then. Now, today we're going to apply what we know about quadratics to real-world scenarios. So we're going to use an equation right here, a formula that we have, because we can model the flying pumpkin by using the vertical motion model right here. Now, what do these variables mean? Well, h of t means the height of an object in feet. The t is talking about time in seconds. The v sub 0 is the initial velocity, in other words, the speed. And then h sub 0 is the initial height of the pumpkin, of whatever the object is, pumpkin or whatever, in feet. So this is where it originally started from. This is the formula that's going to be used. Now, here, look at this. You consider a catapult that hurls a pumpkin from a height of 68 feet at an initial vertical velocity of 128 feet per second. With a partner, answer the following questions. Write a function for the height of a pumpkin, h of t, in terms of time. Find the vertex. What does it mean in terms of the problem? Find the y-intercept of the function. What does it mean in terms of the problem? So now I want you to, with a partner, think about it, and in answering one of these, each one of these problems, put me on pause when you do so. Now, let's go back and let's answer these. Write the function for the height of a pumpkin, h of t, in terms of time. So here would be our formula, our equation that we would come up with. This right here, negative 16 t squared, and then the middle one right here is the vertical velocity, he's talking about the speed per second. And then this is right here where you originally started from, the height. Now for the vertex, you're going to simply just take the negative b over 2a, the AOS, the formula for it, and substitute it in here. So you'd have a negative 128 divided by 2 times negative 16. Get your answer, whatever that is. Substitute it back in here to come up with your vertex. Now, so your AOS was 4, and the height is 324. So what does this mean in terms of the problem? At 4 seconds, the pumpkin will hit a maximum height of 324 feet. So if I were to take this right here and I were to plot it on a graph, then the 4 would be my x, which is time, and that would be my domain, and my range right here would be 324. This is my y. Well, what is the y-intercept? Well, the y-intercept is at 0.68, and what does it mean in the terms of the problem? This is where the pumpkin was first originated, where it was launched from, at a height of 68 feet, and this is on the y-axis. Now, there are some key features and applications, such as the vertex, which is identifying the minimum and maximum of the given situation. We've been going over all of these for the last few weeks. Now, the axis of symmetry is talking about the x value that gives the minimum or maximum, which is normally time. And the y-intercept is the initial position. This is where you started from, or amount in time equals 0. So when we look at this, in the x-intercept is when the situation reaches 0. 0 could be at ground level. When does it reach 0? Now, this is just one instance of the real-world applications involving quadratics. Can you think of any others? Think about it. Well, I have put together some other pictures. So right here, do you recognize this? The arch in St. Louis, Missouri. Well, I've been up in there and it's really neat. And you can feel the wind swaying that some. Not so much you can't stand up, but you can still feel it. And it does give you an eerie feeling being up there. But that is a negative parabola. It opens down. Now here's another one. Look at this right here. So you see this? This right here is a parabola. And look at someone shooting basketball. Do you see that? The arch right there. And this is a negative parabola. And then right here you have, this is the Sydney Opera House in Sydney, Australia. And I've actually been there. It's really neat to see. And it's really pretty inside. But this right here, these are parabolas. And when the person who was coming up with the design, he was thinking about, well, he was peeling an orange in his hand, and he was thinking, as he was peeling it, oh, that's really neat. So he designed the Opera House right here after peeling an orange. Now, I want you to try this out. Look at number 1. Franco is building a rectangular roller skating rink. The area of the rink can be represented by the function a of x equals a negative x squared plus 90x. What is the maximum area of the rolling rink? In number 2, a watermelon is hurled from a catapult that is modeled by the equation right here. What is the initial height of the watermelon? What is the maximum height of the watermelon? How long does it take the watermelon to reach the maximum height? What time did the watermelon reach its maximum height? Now I want you to put me on hold and pause me while you figure these out. Now let's go back over these. So looking at this right here, look at number 1. You've got a of x equals a negative x squared plus 90x. So the first thing you're going to do is use your AOS formula, negative b over 2a. So negative 90 over 2 times the negative 1. And you will come up with 45. Now, once you get the 45, substitute it back in here, right here, and you have a negative parentheses 45 parentheses square plus 90 parentheses 45 parentheses. And you will come up with this answer of 2,025 feet. Look at number 2. On number 2, you've got a watermelon that's hurled from a catapult that is modeled by this equation right here. What is the initial height of the watermelon? So this is where it originally started from. You see this 40? This is the watermelon is 40 feet up in the air when it first is launched. Now to get the maximum height of the watermelon, you're going to have to take and find your AOS first. So you're going to look at this right here, and you're going to say negative b over 2a, and negative 64 over 2 times the negative 16 will give you 2. So when you substitute 2 back in here, negative 16 parentheses 2 parentheses square plus 64 parentheses 2 parentheses plus 40, you'll get 104. Now, we have already answered letter C. How long does it take the watermelon to reach its maximum height? And that was 2 seconds. And what time did the watermelon reach its maximum height? It's still the same thing. Whichever way they ask it, it still means the same thing. So we have 2 right here. It took 2 seconds for the watermelon to reach its maximum height of 104 feet. We could write this as an order pair, parentheses 2, comma, 104, comma, parentheses. Now let's look at some real world problems right here. Look at number 1. You've got a catapult which hurls a grapefruit from a height of 24 feet at an initial velocity of 80 feet per second. And you have this right here that talks about and puts it up into a formula, an equation for this situation. So the first thing you're going to do, you're going to represent the height of the grapefruit, h of t, in terms of the time t. What is the maximum height of the grapefruit? What time did the grapefruit take to reach its maximum height? What do these numbers mean in context to this problem? Pause me when you come up with this. Now, let's look at number 1. So on number 1, you're going to, first off, you're going to have to use the negative b over 2a. And when you put this into the calculator, it'll be a negative 80 over 2 times the negative 16, which will give you 2.5 seconds. Now, you're going to substitute the 2 back in place of the t right here. And when you do, when you have a negative 16 parentheses 2 parentheses 2.5 parentheses square plus 80 parentheses 2.5 parentheses plus 24, you'll come up with 124 feet. That's the maximum height the grapefruit reached. It started at 24 feet. Now, what time did the grapefruit take to reach its maximum height? Well, you've already answered that. It is simply 2.5 seconds. Now, if you were to write this as an order pair, it's going to look like this. And when you have to explain what do these numbers mean in context to this problem situation, this real-world scenario, it means it took 2.5 seconds for the grapefruit to reach its maximum height of 124 feet. Now, look at problem number 2. On problem number 2, you've got a rocket that's launched from the ground at an initial velocity of 112 feet per second. You're going to use this equation right here to represent the height of the rocket, h of t, in terms of t. Now, go through here. just like what we did. What time did the rocket reach its maximum height of 196 feet? What time did the rocket take to reach its maximum height? So go through here and answer these, and so pause me when you do so. Now, the first one is 196 feet. It's already there for you. So we had to take a negative 112 over 2 times a negative 16, and that gave you 3.5 seconds right here. Once you got to 3.5 seconds, you substituted in place of the t's right here. Remember, put it in parentheses, and it gave you 196. And so, yes, these two are the same thing. And if you were to write this as an ordered pair, you'd come up with 3.5 parentheses with the comma 196, and they're in parentheses. And what does it mean in context of this problem situation? It took 3.5 seconds for the rocket to reach its maximum height of 196. Now look at problem number 3. You've got a catapult that hurls a pumpkin from a height of 32 feet at an initial velocity of 96 feet per second. You have the function h of t, which is a negative 16 t squared plus 96t plus 32, which represents the height of a pumpkin, h of t, in terms of time, which is t. Now I want you to come up with the maximum height the pumpkin reached. How long did it take the pumpkin to reach its height? Now I want you to write it as an ordered pair, and what do these numbers mean in context to this real world situation? Pause me while you do so. Now, when you're looking at this right here, the first thing you're going to have to do is to use the AOS formula, negative b over 2a. So when I look at this right here, I have a negative 96 over 2 times the negative 16, and when you hit enter, it will give you 3. Take that 3 and substitute it back in place of the t right here, and when you do, it will reach 176 feet. The pumpkin, this is the maximum height for the pumpkin. Now, how many seconds did it take? Well, it took, this one should be 3 right here. It took 3 seconds. This is wrong. So this right here should be 3 and not 2.5. And this right here also should be 3. So this is 3 seconds and this is 3 seconds. I forgot to change it. Sorry about that. Now it took 3 seconds for the pumpkin to reach its maximum height of 176 feet. So this should be 3 and that should be 3. Down here in the sentence, it is correct. Now look at problem number 4. You've got a rocket that's launched from the ground at an initial velocity of 150 feet per second. The function h of t equals the negative 16 t squared plus 150 t, which represents the height of the rocket, h of t, in terms of t. What is the maximum height of the rocket? How long did the rocket take to reach its maximum height? What do these numbers mean in context of this problem situation? Put me on pause when you come up with this. Now, let's go back and let's look at this. When you're looking at it, the first thing you're going to do is say a negative 150 over 2 times a negative 16. And that is going to give you a 4.6875. You're going to substitute it back in place of the t right here. And when you do substitute it back in place of this, you're going to come up with a really long number. 351.5625, and you're going to round it off. So it would be rounded off to 351.6 feet. Now, how long did it take the rocket to reach its maximum height? Well, that was 4.6875 seconds. Write it as an ordered pair, and it looks like this. And what do these numbers mean in context of the real world situation? Well, it took 4.6875 seconds for the rocket to reach its maximum height of 351.6 feet. Now, these are just some of the real world situation problems that we come up with. How can we use the characteristics of function, quadratic functions, to analyze real world scenarios? Can you think of any? Think about it. Give an example of a type of problem that could be modeled by a quadratic function. Think about it a second. What I come up with is look at a water fountain that's here at school. You see the arc, the arch of the parabola when the water comes out of the water spigot. And think about also if you're a fireman and you're battling a fire and you've got water coming out of the hose. That is a parabola. That's the shape of a parabola. So quadratics are everywhere that you see.